Hello and welcome back to Engineering 211 Statics, and we had talked last time about working with moments in 3 dimensions using the cross product and so forth. And as we finish up our work specifically on moments, I mean, most of our problems going forward will have moments in them, but as we finish up studying moments for the sake of studying moments before we start to combine them with other elements of this study, I wanted to talk about a specific type of moment called a couple or a couple moment. And we see here what I've written is that the moment produced by 2 equal and opposite non-collinear forces is known as a couple. Sometimes they'll call that a couple moment. Sometimes people will use the term couple interchangeably with moment. I will try and avoid that. But let's see what's meant here. I think when I introduced this, I initially talked about you have maybe a jar lid or something like this where you had a force like this and a force like this, and that's going to create some rotational tendency. And technically those 2 forces, if this is, let's say, 10 pounds and this is 10 pounds, they're equal, they're opposite, and they're non-collinear, so we'd have an example of a couple. Let me be a bit more general about this. Let's say that we had a body here and we had some point O, and it wouldn't necessarily need to be on the body. I've placed it on the body, but there's really no requirement that it's on the body. And let's say that we look at a couple of forces here. I'll say that I have this force F in that direction, and we'll say that in the opposite direction I have this force here F. So those forces are equal in magnitude but opposite in direction. And we will say then that they are separated by this distance. We'll say this distance is D. And maybe we'll say that this distance is A here. And this is a right angle, and that's a right angle. So if I wanted to look then, investigate the moment about O, I could say that that was, if I was looking in the clockwise sense, that it's equal to the force F, because this end's going to tend to rotate it clockwise, F times the distance D plus A, and then I have to subtract off this one, minus F times the distance A, right? So if I do the math here, I've got F times D plus F times A minus F times A. Those last 2 terms cancel, and I have the moment about O is equal to F times D, which is an important point. It really is not reliant upon this distance here. This is the couple. And the moment of the couple is the same everywhere. If I were to find the moment of the couple here, if I were to find the moment of the couple there, like I said, if I were to find the moment of the couple off the body, it would be the same everywhere. It's actually a free vector. When we started doing our introductory work on vectors, we talked about free vectors. I'll say now and then it's a free vector. It's going to become very important when we get into equilibrium, that if I'm considering things at this point or this point, I will have to consider that vector the same. It's a free vector. You notice it does not rely on that distance A. So we really just say it's the force times the perpendicular distance between those. We'll do an example with vectors. This works every bit as well with vectors, and I'll show you how that works when we get into that example. Let's try it on a scalar example before we get there. So what we might be able to do with this, a couple of things. Maybe I'll back up one sheet here. I don't want to. Conceptually, what we can do with this is, let's say that we have a body here, and we have a point, and I have a force applied here as F. I could, if I wanted to, say that this would be equal to this same body, and I'll have this force applied, F, and then up at this point I'm going to take and I'm going to apply a opposite force like this, F, And you might say, well, you can't just apply an opposite force. Well, I'm going to balance that out. So I'll apply one this way. Those two should cancel each other out, and I can easily get back to this. Well, now, and what I've done here is if I look at this one here and this one there, that's two equal and opposite forces. And if they have some perpendicular distance, let's say d between those, I could reduce this and say that this is the same situation as a body that has this remaining force, F, left, and a couple moment. It's going to be clockwise here. Then that's going to be m, which is going to be equal to the magnitude F times the distance d. So I could replace this force at a distance with an equivalent force couple system. So this is our force couple system. So let's try that maybe in with a little more detail. So let's say that we have a situation here where I have a lever or an arm. It's hooked to this particular point. Maybe it's on a shaft or something. And we apply a force of 80 pounds back like this. We'll say this angle here is 60 degrees, and let's say that this is 9 inches. Okay, up to there. So you can imagine this maybe an emergency brake lever that you have on the transmission tunnel, or the tunnel, the console between the front seats in the car, and we want to try and figure out what forces and moments are happening down here. So what I could do is I could take this thing and say that I have something like this, where I have this 80 acting like that, and I'm going to then say that I have that 80 here, and I'll just like in the previous problem, I'm going to add and subtract 80. So there's 80, and there is 80, and I'm going to take those and those. I wanted to say couple those up, but that would be confusing. And I can look at this distance. That's going to be what? 9 times the sine of 60. So now what I can do is I can say that I have this, and I can reduce this to this remaining force here, 80. So I've got 80 pounds, and then I have this moment here, this couple moment, that's going to be equal to 80, that's the force, times the distance between them, 9 sine 60, which gives me 624, and what do we have? Pounds and inches, so that will be pound inches. Okay, so what I have successfully done is reduce this force at a distance to an equivalent force moment or force couple system. And this could be really useful. I mean, if we have to design the attachment here, no one likes to pull on the emergency brake in a panic situation and have it shear off and you're left holding it in your hand. So this force here could be very useful if we're trying to design that attachment. And if we're looking at keying this onto the shaft or making sure that this lever doesn't come separated from the shaft that is actuating, this moment could be very important. So I think that's an important step in analyzing that problem. A lot of you may have conceptually made those jumps on your own, and that's fine, but I think it's important that we talk about those and make sure that everyone's reading along the same on that. Well, let's try this in a little more different little more different context, a little more difficult too context. Let's say that I have some sort of a system here. Maybe I have a pipe or a bar, and I have then a couple of wrenches attached here. And all of our dimensions are in millimeters, so all of these large numbers are in millimeters, and we can choose to work in millimeters or meters as we go on. But on this wrench, I have applied a force that's 25 newtons in the upward direction, so in the K direction, in the Z direction. And here on this wrench, I have applied a force that is 25 newtons in the minus Z direction, or the minus K direction. We'll say that this is point A, where that force is applied to that wrench, and this is point B, where that force is applied to that wrench. And I mean, it wouldn't necessarily need to be a pipe and wrench arrangement. This could be a structure of some sort with two equal and opposite forces. We have recognized that these are equal and opposite, so there must be something about a couple here. So let's see if we can do that. I am looking for the moment about O, right? Well, I could recognize that the moment about O is going to be equal to the moment of the couple, because the moment of the couple is the same everywhere. So I could really look at this a couple of different ways. I could say that the moment about O would be equal to the moment of the couple, which would be equal to R from, and this is where people get a little confused. If we take the R from B to A, so let's do that, from B to A, I need to cross that with the force at A. Or if I wanted to go with the R, the position vector, from A to B, I need to cross that with what? The force that ends up at B. So when you do this in 3 dimensions, in 2 dimensions is easy. We just took the force times the perpendicular distance. But here in 3 dimensions, when we're using a cross product, if I'm going to take R going from B to A, I then cross it with the force at A. If then, conversely, I take the R from A to B, I have to cross it with the force at B. And I hope I've got that correct. From B to A, and then A to B. Yes. Okay. So let's try this then. I think I'm going to do this one. Yeah, why don't I do this one? You could do either one. You may want to. I'm going to do this one and then a different method to hopefully convince you of this relationship. And you can come back and try this one here on your own. So let's talk about this R from A to B. What's that going to be equal to? If you imagine yourself at A, how do you get to B? What's that? Minus 350 in the I direction. Does that do it? Minus 200 in the J direction. And plus, we're still in the XY plane, so 0 in the K direction. Does that make sense? You're at A. How do you get back there? You're going to have to go 200 and 150 gives you minus 350 in the X. And then how do we, we're out here 400, and we need to get back here just 200, so we're going to have to go minus 200 in the J. So that seems to work. The F is easy in this. F sub B is really just plus 25 in the K direction. So when I put those together, I could say that this is equal to I, J, K. I'm going to have minus, I think I'll do 0.35. I'll convert to meters so I don't have such large numbers. Minus 0.20. And then this one I have 0, 0, and 25. When you get done with that, that turns out to be minus 5 in the I direction plus 8.75 in the J direction. And that would be Newton meters. Okay, so that would be our answer. That would be the moment of the couple, which has to be the same as the moment about O. Now, I'm not going to do this one here, but you could do this if you were to switch up this. So from B to A would be positive, positive, and doesn't matter, but negative. And then this one here would be negative, right? Because you'd be the force at A. Well, if you invert the signs on this and invert the signs on that, you will mathematically have to get back to that. But that would be good practice for you. What I would like to do is maybe go to this moment about, oh, some of you might have, had we not talked about couples before, you might have said, well, hey, I'm just going to define this r vector that goes from there to there, and then I'm going to define another r vector that goes from there to there, and add them up. And you would be perfectly fine doing that. Let's see how that works. So here is 4. Maybe I'll look at this like this. Hopefully I have enough room then. So I could say that the moment about O would be equal to R from O to B crossed with the force at B plus R from O to A crossed with F sub A, right? So what does that look like? Well, we're going to have, maybe I'll just drop straight to the vector form. So let's see. You imagine yourself at O. How do you get to B? You're going to have to go 300 in the X, right? So that's 0.3. How far are you going to have to go in the Y? This is Y. So you're going to have to go 200.2. And that is 0, right? And when you get there, what's F sub B? That's 0, 0, and 25. It's positive up. So then this one, you're going clear from this O, clear out here to A. So you're going to have to go how far out here? 300, 150, and 200 is 650. So 0.65 in the X. In the Y, you're going to have to go out 400.4. Still nothing in the K or the Z. And then our force when we get here is pointing down. So I have 0, 0, and minus 25. Okay. So now when you go through the crossing on this, you got a lot of zeros, so if you did it by hand, it would not be too difficult, but you should come up with exactly the same result, which is minus 5 in the I direction plus 8.75 in the J direction. And again, that will be Newton meters. Okay, let me double check that real quick. Calculation here. Yes, I think we're good with that. So the nice thing about that, I wouldn't say that this is a proof. You never want to try and prove something with numbers. You always would do an aside here. You don't want to prove the classic thing when students want to try and do a proof with numbers rather than with variables, is to talk about 16 over 64. That works in that one, but you don't want to go in. Get into that business. So certainly not a proof, but a nice demonstration that the moment of the couple is really going to be the same everywhere. So we could either find the moment about O directly, or we could do like we did initially, find the moment of the couple and recognize that that's exactly the same. So hopefully that's useful, a good practice. I'd like to look at one last concept here, the equivalent force couple system, and we've talked a little bit about that as we introduced this. A place where this comes in a lot is in structural work and whatnot. Let's say that we have a cantilevered beam, and we apply a force here. So maybe we have 1,000 pounds, and this is 10 feet, and we'd like to come up with the equivalent force couple system back here where it's supported at O. What are we going to have? Well, if we were to look at that, we're going to, at this point, and I've separated just by a little distance there for clarity, so I'm not right down here, but we would have this force. The force would be exactly the same. We would have 1,000 pounds down, and then we have this couple moment here. What's that going to be equal to? Well, I mean, you could go through the process if you wanted to, and so we have this 1,000 acting like that, and then I could put a 1,000 up here and a 1,000 down there. I have between those a couple that is 1,000 times 10 feet, so I have 10,000 pound-feet, and that's going in what direction? If you look at that, no matter, I mean, if we pin that here, it's going to rotate that way. If we pin it right there, it's going to rotate that way. So this is always going to be rotating like this. So we could say that this was then 10,000 pound-feet. Okay, 10,000 pound-feet. So anyway, that is a good example of coming up with an equivalent force. So we've reduced this system here to an equivalent force system, where I've got this equivalent force and I've got this equivalent couple or moment. If you go to designing this connection here, we're going to talk spring term about, well, to some extent we'll talk about it also with shear and moment diagrams in this class a little later on. We'll talk about the shear through this, which this number would be very important, and we'll talk about the moment, the bending moment at that point, where that would be important. So we will need both of those numbers, and coming up with an equivalent force couple system is important for that. Well, where we go next time, we're taking a big change. You may have noticed that we skipped Chapter 3. So we've done Chapter 4, and we're going to come back and we're going to look at chapters... I'm going to look at chapters... Not doing real well with my writing here again. We're going to look at chapters 3 and 5 really simultaneously, which is going to take us into equilibrium. Okay, equilibrium, and from that we're going to get our equations. We're going to talk about developing the equation. The sum of the forces in the x direction is equal to 0. The sum of the forces in the y direction is equal to 0. Sum of the forces in the z direction is equal to 0. We can talk about the sum of the moments about the x-axis is equal to 0, and the sum of the moments about the y-axis is equal to 0, and the sum of the moments about the z-axis is equal to 0. We'll actually pick these two and then this one and this one, and that will give us our two-dimensional problems that we'll pretty much concentrate in and look at. So we'll look at some of the forces in the x direction, the y direction, and then some of the moments, which is technically about the z-axis if we're looking at that. And we'll be able to solve lots of problems with that. The one thing that we have to be careful of is the summation. That really means all forces or all moments, so we don't want to leave any out. So we're going to have to talk about the free body diagram, where we get to try and separate a body from all of its attachment and replace those attachments with forces so we can have a proper accounting of those forces. Because as you could see here with the summation, if you're one force off, you're going to be off by quite a bit. So that's where we're going to go as we go forward, and we look at equilibrium. We look at Chapter 3, which is very important. Don't take our skipping Chapter 3 in the textbook as making the material unimportant. I just chose to talk about moments, and then we're going to look at Chapter 3 and Chapter 5 simultaneously in terms of equilibrium. That will be very important, and that's where we will go when we get together next time. Take care till then. Thank you for watching.